Hello, and welcome to this ESPEC North America webinar. My name is Matthew, and I will be your Global Spec moderator, and I want to review a few housekeeping items with you before we begin. Please take a moment to familiarize yourself with the operation of the user interface for today's webinar. The large window with the heading Presentation, in the upper left, is the primary window for today's session. Just to the right of the main presentation window is the Speaker Bio window, with background information on today's presenters. Just below that is the Q&A window. At any time during the presentation, you can enter a question into the box in the lower section of the window and click Submit. Your question will be placed into the queue to address when we get to the Q&A session. At the bottom of your screen, you will see additional buttons to enhance your webinar experience. To see what a particular button does, just place your mouse pointer over it and a tooltip will appear with a description of the button's function. Now I would like to hand the presentation over to David Young, Marketing Manager for ESPEC North America, to introduce the webinar and presenters. David, please go ahead.
Welcome to Level Up Your Temperature Testing webinar by ESPEC North America. I'm David Young, Marketing Manager in Michigan. We assume that you know something about using temperature testing to find the problems with your product. Many times, companies that are testing their products just start with the range of temperatures it's specified to work in, and they might use humidity as well. But we see companies get their product out in the field, then scramble to buy additional chambers from us because they're experiencing high failure rates. And then they also want to do powerful testing, more than just meeting the minimum. We wanted to help you avoid the scramble, to better understand the range of temperature testing equipment, what resources it requires, and the benefits you should be looking for. In video games, leveling up may just cost you time in repeating the same level or paying for additional weapons. In the product quality game, the costs are similar in time and money. But like games that limit what your character can carry, you can't just buy a super fast test chamber without the knowledge or resources to use it. We're going to target these topics head-on to help prepare you for moving from simple simulating to stimulating and stressing your product and level up the effectiveness of your testing. For now, we assume you're stuck on your current level of testing, but the boss keeps you from leveling up. What's a boss? It's that super powerful enemy at the end of the game with multiple weapons and maybe multiple heads that needs to be shot repeatedly to be destroyed. You just mash all the buttons, hoping to take him out. We want to help you be prepared to beat that quality boss and improve your product. Our presenter today is Neil Dordenbach. He's ESPEC's Senior Application Engineer at our Halt testing lab in Colorado. He's helped hundreds of products level up for improved quality prior to or after launch.
Thank you, Dave, and thank you all for joining us here today. I'd like to kick off our discussions about how to level up your environmental testing, first by taking a look at thermal cycling. Now, I'm sure most of you are quite familiar with thermal cycling. It's a common stress that is used in environmental testing, and the stresses that are induced in electronics due to thermal cycling are very well understood. It's the cornerstone of much of the traditional reliability demonstration testing that is done, as well as environmental stress screening done during production. There is a key problem with thermal cycling, however. It can take a long time, especially when your products are extremely high reliability products, and you're trying to demonstrate that you meet those high levels of reliability. It can take hundreds of thermal cycles and hundreds of hours to meet those testing requirements. And this can be a serious problem when your timeline is short, when you're trying to get things out the door. If you look at, for example, requirements for solar panel testing in IEC 61215, they're talking about 10 to 200 cycles that could take up to 10 days. Looking at those requirements. If you look at IPC 9592A, those are recommendations for requirements for power conversion devices If you have Class 1 devices, they say 300 thermal cycle tests are necessary for validation. If you have a Class 2 device where you have high performance and extended life requirements, you can be looking at up to 700 thermal cycles. That takes a whole lot of time. Fortunately, there's ways to speed that up. Now, if you're doing your thermal cycling in a traditional thermal chamber, you're probably looking at thermal ramp rates on the order of 5 degrees C per minute. If you're moving to systems with cascade refrigeration, it's possible to get to the 10 or 20 degrees C per minute range. But even at that, it's going to take some time to get these reliability demonstrations completed, especially if you're looking at those hundreds of cycles of testing. But it's possible to move to a chamber with faster ramp rates so that you can get this testing done more quickly. If you look at a chamber that has direct inject liquid nitrogen cooling, that's a very aggressive method of cooling. And combine that with high-speed airflow inside the chamber and lots of open element nichrome heaters for the heating side, and you have a chamber that can reach 60 to 70 degrees C per minute ramp rates, actually measured on the product. With ramp rates like that, you're able to complete your testing much more quickly. Not only that, there's a second key advantage. If you are ramping more quickly, your ramps are more stressful, so you need fewer ramps in order to get the same level of fatigue on your product. So not only are you getting done more quickly because the ramps take less time, you're having to do fewer cycles as well. Now, this logic is outlined in Mill Handbook 344A. There's a section there describing screening efficiency calculations. And the idea is that you look at what ramp rates you're doing for your thermal testing and what extremes you're going to, and also what your vibration testing is like. And it calculates a number that is supposed to tell you the efficiency or the effectiveness of the screen. That is, what is the likelihood that it will catch a defective component and prevent it from shipping if you run a screen with these levels of stress. Now, the actual numbers that come out of those calculations for screening efficiency aren't too valid anymore. This was written, I think, in 1985. It is based on a whole different class of electronics than we're using now, but it does give us a nice way to compare the stressfulness of different screens. So we can look at what a 5 or 10 degrees C per minute ramp rate result, what kind of screening efficiency that results in, and then take a look at what it will take to get that same screening efficiency at faster ramp rates. And that's what we'll do in the next slides. Now, this slide shows 20 thermal cycles being done with ramp rates of 10 degrees C per minute. If you run these, and they're running from about minus 55 to plus 72, it looks like. If you run those numbers through the screening efficiency calculations, you come up with an efficiency of 0.99996. Now, again, that's 20 cycles running at 10 degrees C per minute. Now, if you run those ramps at 60 degrees C per minute ramp rates, you wind up achieving the same precipitation efficiency with just 5 ramps. Those 5 ramps are happening a lot faster than the 5 ramps at 10 degrees C per minute. So you wind up saving a remarkable amount of time by moving to the 60 degrees C per minute ramp rates. So here you can see those two graphs overlaid, where you see the same screening efficiency happening in 5 cycles, taking about 150 minutes. And if you're running at the slower ramp rates, taking over 1,000 minutes to achieve that same screening efficiency. And you'll note if you take a look that those 5 thermal cycles are occurring in less time than it took for 4 of the slower thermal cycles to happen. So, faster ramp rates, faster ramps, and needing fewer ramps. Now, when you're gaming, you're going to run into that boss enemy, the very powerful enemy that's very difficult to bring down. If that particular enemy happens to have sensitivities or weaknesses to two different types of weapons, and you can work with a co-player with both of those weapons to bring it down, those weapons will have a synergistic effect, and you're able to bring down an enemy that you couldn't bring down with the individual weaponry. Well, the same thing happens when you're working with stresses and environmental stress screening. Very often, the ability to combine stresses is the key to finding the defects that you need to find in the amount of time you have to find them. In general, thermal and vibration stresses are synergistic, and they will drive out failure modes more quickly than either one of them can alone, and find failure modes you can't find by using either one of those stresses alone. So, the next powerful level up for your environmental testing is to add in vibration. Combine those stresses so it multiplies the effectiveness of what you're doing with the product. The tool that is most commonly used in combining thermal and vibration stresses is repetitive shock vibration. These repetitive shock stresses give you fatigue in multiple axes simultaneously. That speeds testing even more. So by being able to get a product exposed to these thermal extremes, exposed to the very fast thermal ramp rates, and the shocks from the repetitive shock vibration system all simultaneously, you can bring out those failure modes that you can't find any other way. Now here is a graph that can give you an idea of the true effectiveness of combining stresses. This graph represents data taken from Halt testing, highly accelerated live testing. And in this testing, the product is subjected to first cold, then hot thermal steps, then rapid thermal testing, rapid thermal cycling, then vibration at ambient temperatures, and then finally a combined environment of thermal and vibration. And in all cases, the vibration that's referenced is the repetitive shock stresses that I talked about earlier. And in these tests, broke down exactly what stresses induced what percentage of failure modes. As you can see from this graph, between the cold and the hot stresses, we've got about 40% of the failure modes. Vibration and rapid thermal come into almost 70% of the total. But when you combine the vibration and thermal, you get the final 32% of the failures that were found in these tests. So what this data is telling us is that we'd miss about a third of the failure modes that could exist in a product if we weren't able to combine the thermal and the vibration stresses. Now, we've talked about the value of doing rapid thermal cycling as part of your environmental stress screening, and the significant added value when you combine vibration with that thermal cycling. But now, what do you do when you need to take your testing up yet another level? You need a character with mega health, when failure just isn't an option. Well, this is when you learn that stressing to failure is how you find out how to stay alive. When you're playing, if you're not willing to let your player be beaten, then you never learn how to make your player better. Every lost battle is a lesson in how to win. To gain those same lessons with your product, it's necessary to test to failure and to use stresses typically that are outside of the normal use stresses for that product. These are the basic building blocks behind Halt, the highly accelerated live testing, to use stresses beyond specification and push the product to failure so that you can learn how it fails, then take that information to come back and improve your product. Now here you see the main building blocks of a halt test. From the beginning, we talk about subjecting your product to increasing levels of a stress. One of the key words here is increasing levels. We're increasing the stresses in a stepwise fashion, dwelling at each level and doing functional tests at each level. So we're not necessarily hitting it with just great big hammers. We're hitting it with progressively larger hammers so that the very weakest things fail first. We learn what the true weak links are in the product. And we step through the stresses, going from least destructive to most destructive stress. So we start with thermal stepping, cold and hot. Then we do rapid thermal, going back and forth between the limits we found in step testing. Then we do vibration at ambient. Then we do combined testing. In all cases, we're testing under stress. That is, the product is being functionally tested while it's in the system, while it's undergoing those stresses. That is critical to finding the soft failures that go away when you take the stress away and wind up turning into no defect found failures from the field. Once you find these failures, you figure out a way to get around them or work through them and continue testing until you've learned everything that Halt can show you. And that happens when you hit the fundamental limit of the technology. That's the point where in Halt we say we're just not getting valuable failure modes anymore. We're not learning from the failure modes. We've reached the point where a complete redesign is going to be necessary to get past these failure modes. That's not what Halt is about. It's about finding the easy-to-fix failure modes that will improve the reliability of the design. Now, here are some of the key concepts behind Halt testing. You'll see that Halt is a very different kind of test from what you may be used to doing. If you're used to doing design verification testing or reliability growth testing, those obviously are tests that you have to pass, and there are very clear, established limits to the stresses that are applied during those tests, and you certainly expect to get through those tests without any failures happening. With Halt, all of that gets turned around. It is a failure-oriented test. The goal in Halt is to drive your product to failure so that you can learn from those failure modes. Consequently, you don't ever pass or fail Halt. There's no pre-established limits set up that once you reach them you can say, there, we went far enough, I passed Halt. Doesn't work that way. You keep going until you find failure modes. Really, the only way to fail Halt is to not find any failure modes. Then you haven't gotten the value from the test. It's a discovery process, a chance to find out how your product will fail in the field. Now, here are a few more of the key concepts to help you understand what Halt testing is all about. And this first one really is a very important one. Halt does not replace any of the design verification testing, reliability growth testing, live testing, all of the tests that you normally do on a product before product release. Those tests have very specific and critical purposes, and they must be conducted. They're designed to demonstrate that the product will function in its intended environment, that it has the reliability level that is desired, that all of the elements of the design work as you intended. But the critical thing here is those are all validation tests of one kind or another. Failures during those validation tests are extremely expensive and extremely undesirable. These tests are happening very near the end of the product design cycle when the product is very near release. And if you find failures there that require design changes, you're restarting processes that are going to push out product release. And as we all know, that can be a very undesirable position to be in. If you do halt before you start these validation tests, now you're getting some extreme value from the testing because you're eliminating failure modes, not only ones that might show up in the field later, but ones that might stop your design verification testing halfway through. Might make your reliability growth testing take an extra 2 or 3 or 4 weeks. If you can eliminate those failure modes and get into those validation tests and fly through those validation tests, now you've really gotten some value from the halt. Not only do you have a more reliable product, but you're releasing that product faster. It's getting through the whole design validation process more quickly. Halt is your chance to identify and eliminate design issues early and fast, so you can fix them when they're cheap and easy to fix. So when we're talking about Halt, we say we are not trying to simulate the end-use environment. We're trying to stimulate failure modes very quickly. So we're not simulating, we're stimulating to destruction. So the first step in Halt is to not follow the rules. You ignore the specifications on the product, and you forget the intended use environment for the product. It doesn't matter whether your product will ever see these stresses in the field. What matters is that the failure modes we're finding are the weakest links in the product. They're the things that are failing first. We will step those stresses up then. Keep stepping up the stress until we find operational and destruct limits for the stress, and then step through the stresses, starting with least destructive and going to most destructive. We order them in that way so that we get as much information as possible from each sample. So we'll begin with cold step stressing. As a general rule, electronics likes cold, so we don't find too many hard failures in cold step. Then, once we've learned all we can going cold, we'll turn around and step hot. In all these cases, the steps are in 10 degree C increments, and we dwell at each step for 10 minutes, and then do a full functional test at the end of that 10-minute dwell, so that we can demonstrate that the product has passed that level of stress and lived through that dwell. Then step up the stress again. When we find failures, well, the first thing to do is back the stress off and see if we have found an operational limit, see if the product recovers when the stress is taken away, or perhaps we found a destruct limit, a hard failure, the product doesn't recover. Document those failure modes, learn as much as we can from them, and move on, continuing through those stresses, and you don't stop until you can't learn any more from the failure modes. The idea of the testing to the fundamental limit of the technology is a little theoretical, in my opinion. It's hard to exactly say what the fundamental limit of a technology is. Really, you're stopping when an engineer looks at the failure modes you're finding and says, I can't do anything about these without spending a whole lot of money. There's no way to get around these. And that's not the point of Halt. The point of Halt is to find tolerance stack-up issues, or the one particular component that comes off in vibration first because of the way the leads are bent, or basically cherry-picking out the easy-to-fix, easy-to-identify failure modes that will be the ones that show up first in the field. So you keep going until you've got all the failure modes you can get your hands on, and then comes step 4, really the most critical step in Halt, the failure analysis. It is very important to understand all the failure modes that happen in Halt. And keep in mind that saying, well, of course it failed, it was beyond specification, what did you expect, is not failure analysis. It is the quite understandable, often immediate reaction from a design engineer who sees a failure that happened way outside of specification, but understanding what caused that failure to happen means you're understanding the weakest parts of your product, and you're giving yourself an opportunity to have a truly rugged and reliable product. Halt is an extremely valuable tool when you're trying to step up your game in environmental stress testing.
Hello, this is David Young again. I wanted to cover some more information about temperature cycling and the equipment used and what it requires. As Neil said, thermal stress means using fast ramp rates and greater thermal ranges to stimulate your product's failure modes. Your situation may not allow you to embrace the full halt attack with destruction as your goal. So you might just be screening for defective parts or defective manufacturing. That might be more in line with your needs. If your current thermal cycling is only used to get from one temperature to another, speeding it up will be a great saving in test time. But there are other potential benefits. As with the halt approach, the thermal stress from faster cycling can stimulate failure mechanisms for better results. Per Neil's example about the solar panels, fewer cycles were needed because of the test's effectiveness. Or you could consider doing more cycles in the same allotted time and have more opportunity to move beyond infant mortality failures. And you could expand your test's temperature range without slowing down the test. So a test that was minus 20 to 60 degrees could be done from minus 30 to 70 degrees without impacting your current testing time. How fast to go? And how extreme can you expand the range of temperature? That's up to you, and certainly it will take some experimentation. We or other chamber manufacturers can perform calculations for you based on information you provide to identify what chamber heating and cooling capability you will need to do additional testing. We would need to know these things: what your loading is per test, the total mass and material types, and that includes fixtures and wiring. If the load is powered, we'll need to know how much heat it generates, what your start and end temperatures are of your cycles, and what your target ramp rate is. This ramp rate may be measured on product or as air temperature ramp rate. Most performance chambers have the ability to test based on the sample's temperature. With heat generating or large products, this can be a complex decision and worthy of some experimentation. We're pretty cautious about doing on-product rate calculations because of the wide variation of rates depending on the exact sensor placement. Other aspects of Halt methodology can be applied to your current testing regimen. Leveling up by additional stressors such as humidity, power cycling, mechanical stress with vibration or other inputs. You can do live monitoring of the DUT for fault or errors due to intermittent failures. And you can try testing larger assemblies. As the closer you are to the final product, the more realistic the test is going to be. Now is a good time to discuss the different types of chambers. While we sell a lot of humidity chambers, today I was going to focus on temperature cycling chambers, which have a much wider variation and possibility. We have what we just call thermal cycle chambers, which are great general purpose equipment. Air-to-air thermal shock chambers, which are a specialized type of chamber, and the super-fast liquid nitrogen cooled Halt equipment that Neil talked about. Now, the thermal shock is a dedicated type of equipment for instant temperature changes. Thermal shock is commonly used to meet specific test standards and is usually targeting components and not assemblies. It is a transfer or damper mechanism for the instant temperature shock effect. Our thermal cycle chambers are similar to standard environmental chambers, but just have more heaters and a larger refrigeration system. They allow fixed temperature testing and controlled ramping. They can have humidity, and there's lots of flexibility in sizing. Importantly for this presentation, they allow you to test at different ramp rates to see what results you get up to the limit of their performance, which can be anywhere from 5 to 25 degrees per minute. And then there's the Halt chambers with the 60 degree or more change rates and repetitive shock stress. Getting these faster machines can be more power and resources are required. We know how unrealistic those video games are with unlimited ammo. So what limitations are you going to have to deal with these chambers? Well, they're going to need more utilities. The Halt chambers are cooled with liquid nitrogen, and that needs to be hard pipe for full insulation and is a very specialized setup. But small systems can be run off of portable tanks. The expended nitrogen is going to need to be vented as well. The thermal cycles use the refrigeration system to move the heat out of the chamber, and it needs to go somewhere. Air-cooled chambers ventilate the heat directly to the air. Smaller systems can do this in your lab space, if the room can absorb the heat generated. Otherwise, the heat is released outdoors with an air-cooled condenser, kind of like you'd see outside a restaurant or a grocery store. Water cooling can be used instead of air cooling. In most cases today, our customers are not simply using city water to do this, but are purchasing a dedicated water chilling system. There are several types, and selection is dependent on your location and other factors. Electricity can be an issue too, as these systems may require double or triple the amount of power as a standard chamber. In some cases, customers have trouble getting the higher voltage of 480 volt in office or small lab environments. And compressed air is needed for the repetitive shock systems, and it's also used for what we call air makeup in the refrigerated chambers because the air is shrinking quickly as it is cooled. I'd now like to end with a subtle sales pitch on leveling up your quality game. ESPEC has several new models that I think strike a good balance between size and resources required, such as not requiring water cooling, while offering significant ramp rates. These are smaller, of course, and may be worth looking at for pilot testing some of your new methodologies. There's the EQZ4, which is a small Halt system with repetitive shock and refrigerated cooling. 9 degree per minute ramp rates are possible, but with liquid nitrogen, you can get full Halt performance. There's the BTZ 4200, which has 3 horsepower refrigeration and onboard air cooling, and 15 degrees per minute is possible with this. There's also the EGN-Z4 chamber, which is the same size, but has 5 horsepower refrigeration that does require water cooling, but you get 25 degree per minute ramping. Whatever direction your testing program goes, I hope the information that Neil and I shared with you today is helpful as an overview of temperature cycling and what it will take to level up your testing program.
Thank you so much for that great presentation. And now let's get to the Q&A. We have some questions that have come in from the attendees, so we're going to move into answering those right now. If you haven't submitted your question yet, you can do so now by entering it in the Q&A box and clicking Submit, and we'll try to answer it before the close of the session. Okay, now for our first question from the audience. Looks like this one is for Neil. If I test at faster ramp rates, I'll be changing temperature faster than my product will ever see in real life. Won't that give me unrealistic failures? Neil?
That's a good question and a common one when we're dealing with the kind of stresses we do in Halt that are typically beyond spec and beyond what the product would see normally in the field. With the faster ramp rates, we're accelerating how long it takes for that failure mode to happen. There is a chance that we'll uncover a failure mode that
only occurs because of that extreme ramp rate. And the way to distinguish that is with failure analysis. That's the key to deciding if a failure is valid or not. Is do a failure analysis, see if it really is that extreme stress that induced it, or if the extreme stress simply induced it faster. So failure analysis is really the key to the answer to that.
Excellent. Thank you for that. And just want to remind the audience, we are in the Q&A session. We have our experts from ESPEC online and ready to answer your questions, so please send them in. Okay, next question from the audience. Okay, another one for Neil. Is there value in combining humidity testing with vibration and thermal?
Oh, that's another one we'll get on occasion, because we talk about the effectiveness of combining stresses when we combine thermal and vibration, and humidity is another stress that just seems to make sense to bring in there. The trick is that, well, for one, from a implementation standpoint, it's really difficult to combine humidity with direct inject liquid nitrogen cooling, because the nitrogen is continuously purging the chamber atmosphere. So we can't really control the humidity. And it's 100% dry nitrogen environment inside the chamber typically. But we also found that there isn't a real value in bringing humidity into the vibration and thermal environment like that, simply because the failure modes that are induced by humidity tend to be, corrosion-related issues that simply take time. They can't be accelerated like the failure modes we accelerate with vibration and thermal. They obey Arrhenius. They take a certain amount of time at a certain temperature, and really the only way to accelerate humidity testing or get those results faster is by doing humidity testing at higher temperatures under pressure in the pressure cooker type chambers. So there really isn't anything to be gained by trying to bring humidity into that vibration and thermal environment.
Excellent. Thank you for that. You made some great points. Okay, moving along. Looks like we have a question from the audience for Dave. Okay, here it is. We're in a rented building. How much performance can we get with a chamber just running on electricity? Dave?
Okay, yeah, that's a good question. Covered that a little in the presentation, that we have some models can do different things. What we see most people doing, we have the chamber I showed was BTZ 4200 is 15 degrees per minute, and that just runs straight off electricity. And that's going to allow you to get the adjusted ramps. You don't have to do 15. You can do anywhere up to 15 degrees per minute. But what we see a lot of clients doing is jumping right to the thermal shock chambers, which I kind of skipped over in the presentation, because you can't realistically control the ramp rate as much as you can with a thermal cycle chamber. But they do give you the biggest bang for your buck in terms of getting change rates. And there you can look at getting change rates of 20 degrees per minute. And once again, only air-cooled system and doesn't need as much electricity as a bigger chamber. So those 15 to 20 degrees per minute would be kind of the answer to that question.
Excellent. Thank you for that. And I'd just like to remind the audience, we are in the Q&A session. You can submit your question now by entering it in the Q&A box and clicking submit. Okay, next question from the audience. Looks like this one is for Neil. What are the advantages and disadvantages of liquid nitrogen cooling versus mechanical refrigeration?
Thank you. There's several things to look at when you're trying to decide between the two. From a performance standpoint, the liquid nitrogen cooling gives you extremely fast cold ramp rates and a much lower cold limit. The Halt chambers will get down to minus 100 C, and that's, I believe, impossible to do with mechanical refrigeration. And the ramp rates are very difficult to achieve with mechanical refrigeration without getting into some pretty complex systems that require cooling towers and the rest. But the biggest disadvantage to liquid nitrogen is you've got to get the liquid nitrogen into the facility. And depending on the size of chamber you have and how much liquid nitrogen you need, that can mean putting a tank outside of liquid nitrogen, running vacuum jacketed pipe into the chamber location, and paying for the liquid nitrogen and having a truck come up and fill up the tank when you need it filled up. So you almost have to do a spreadsheet on it and look at what are my needs, what will I be missing if I don't get those rapid thermal change rates and those extreme temperatures, and what's it going to cost to get the liquid nitrogen put in versus what's it going to cost to get my mechanical refrigeration up and running and get cooling towers in if I need such a thing, or do I have the cooling water already in the facility? There's several things to look at back and forth there. It actually gets complex enough you might want to have a sales rep help you out with looking at the details of it and getting all the pluses and minuses figured out before you choose a system.
Excellent. Thank you for that. And we have a couple more questions in the queue, so we'll get to them in a moment. But as a reminder, you can still submit your question by entering it in the Q&A box and clicking Submit. Okay, next question. Looks like this one is for Dave. Can I apply the Halt methodology with just a regular environmental chamber? Dave?
Yeah, that's kind of the contrast we did between what Neil was talking about and what some of my presentation was. You take the same thinking you would for Halt and you can apply it to your regular testing. The difference is in the Halt, you're really in a practice mode and you're repeating the same step over and over to get better at it and to find out solutions to getting past the problems that you're having. And once you get past that into the later stages of RAM or after the product's gone live, you don't have that luxury. So you're actually playing with real lives, if you will, in the game scenario where when you lose a player, that's a cost to you. So you're using the same approaches and methodologies, your goals are different, and your costs are more real than they were in the Halt stage, where the isolated failures are things you're actually looking and trying to create as opposed to cause. Only in the worst cases with the later screening type tests. Hope that helps.
Excellent, thank you. Yes, that was great. Okay, all right, looks like we have one last question in the queue for now. So here is our last question for now. Looks like this one is for Neil. What is a realistic lag between air temperature and on my product?
If you've got thermocouples at various locations on your product and you're looking at the difference in the temperature of the air that the chamber's changing versus what's happening on your product, there's a lot of different factors that get into that. Obviously, how much mass, the massiveness, the thermal mass in your product, and how long it's going to take for the temperature change to percolate into wherever you have that thermocouple located. If it's on the surface of the product where the air temperature can affect it more directly, you just have to change the temperature of the very top layer of the product, if you will, in order to get the temperature change. Then you can have a relatively short time lag between air temperature change and product temperature change. The biggest factor in what that difference is can be the airflow in the chamber. If you keep a high-speed airflow going across the product of the air that is at the temperature you're trying to drive to, the product will make that thermal change much more quickly than if the air is simply if the air is not moving across the product but simply stagnant there. So if you have air circulation through the chamber, that will speed that change quite a bit. And you really can't say what a realistic lag is because of that difference between where am I measuring on my product and the rest. But if you're worrying about speeding that up, you want to look at increased airflow and basically letting that air get into more areas of the product and move through the product more quickly.
Excellent. Thank you for that. And that was our last question, so we're going to wrap things up right there. So guys, thank you so much for that great presentation and also taking the time to answer some questions from the audience. I'd like to also thank our audience members for being part of this webinar event. You will be receiving an email from us with a link to the on-demand version of this presentation, so you will be able to come back and watch this again or share it with your colleagues. And lastly, please take a moment to complete the survey, which will appear on your screen at the end of this live webinar. For on-demand viewers, you will find the survey located along the bottom of your attendee console in the survey widget. Again, thank you for taking the time to attend this webinar event. Take care, and we will talk with you soon.